It's Alex from paperairplanes.co.uk here. I'm going to show you one of my favourite experiments from my fluid dynamics lectures when I used to be at Cambridge. Feel free to check out more on paperairplanes.co.uk. So, this is the inner tube from a roll of tin foil, or aluminium foil, or aluminum foil if you're American. You need a cardboard tube, and you need one that's tight enough so that it can actually withstand being wrapped around with rubber bands, and this one probably is the best I've found. The other thing you need is a bunch of rubber bands so that you can make a chain of rubber bands like this. What you want to do is thread the rubber bands through each other, two at a time, and then do this. Again, thread the rubber band through itself so that you end up with something like this, and do that 10 or 20 times, probably 10 times, so that you have a good long chain of rubber bands. I've got those looped over here. Here's the chain of rubber bands, and the idea is you take the tube and you roll the rubber bands around the tube nice and tight. And you roll it over and over and over, and that's what I'm doing just off of camera right now, is you roll the rubber bands nice and tight around. Not too many times, depending on how big an area you've got. I've obviously got a very small area here. The idea of this is that it demonstrates the Bernoulli effect. And so you can see here, the rubber bands have been wound around under, over, and the tube's going around this way. Right? The tube's going around like this to be tightened. And that means that as the tube goes, it will be spinning in this direction and moving in this direction. Sorry, it will be spinning in this direction, right? Because it gets pulled from underneath, which means this gets sucked under and the top goes backwards, bottom goes forwards, top goes backwards, and the tube itself is going forwards. And the air moves with the surface of the tube to some extent, creating a bound vortex around the tube, which means the air on the top of the tube is moving in this direction, the tube is moving in this direction, and so the air in the room is effectively moving in this direction versus the tube too. So the air in the room is moving this way, like this. The air on the top of the tube is also moving this way, but the air on the bottom of the tube is moving in the other direction, which means net, the air on the bottom of the tube is moving slower, and the air on the top of the tube is moving faster, which results in the Bernoulli effect lift, right? Fast-moving air has lower pressure, slow-moving air has higher pressure. And we used to have it demonstrated in our lecture theatres like this, with someone just sitting on the other edge here, and the professor would say, "Oh, which way up do you want me to let go of it?" So here goes. You see that? I released it flat and it went to the ceiling. I'll just do it again. See if it works twice. It's been very embarrassing as I've been making this video because it's failed repeatedly and I had to practice a bunch. I'd be a terrible professor. Okay, let's go again. Just wrapping the rubber band around. And there you go. Bernoulli effect demonstrated with some rubber bands and a piece of cardboard tube. Perfectly cylindrical.